Today I want to be focusing on quantum mechanics. Now, I'm going to give you a bit of a warning. I am not by any means an expert in quantum mechanics. I have a very small grasp on it, and I would willing to share my small grasp with you guys in case you want to get interested. There's a lot of media out there online that talk about it. Quantum mechanics started with a guy named Planck. And what he discovered was that energy is not continuous. That is to say that energy cannot exist in any set number of states, but it is confined to a certain number. So there's a very, very small value of energy, which is the smallest energy you can have. You can't get any smaller than that. And all other energy is derived by multiples of that. So if you had 20,000 of these particles together, then you'd multiply that energy off by 20,000 and you get the new energy. And the reason we didn't notice this for a very long time is because it's so small that we thought it was continuous, but it's not in reality. And the same thing was done for chemistry. Chemistry was quantized, or that is to say, matter was quantized into the atom being the smallest possible particle, and then everything else being built up of thousands and trillions and a whole bunch of these atoms on top of each other and built together. And when we can only see really large parts. But there is a finite set that you can't get any smaller than that. That's the same idea with energy. And we can't see when we look at things that they're made of atoms clearly. And when we look at energy, we can't see that they're made up of small little bits. So big deal, right? Energy is just small integer things. It doesn't really change anything, does it? Well, it does actually. It changes lots of things. What happens is that energy is now small particles of things that interact with matter. Well, what does that mean? Well, it could mean a whole series of things. How many different particles are there? Are they all the same particles? There's a whole bunch of questions that got arise at this point. And what was eventually decided was that the four fundamental fields of physics, which consist of gravitational, the strong nuclear force, the weak nuclear force, and the electromagnetism, those four fields should each have their own particle that go along with it. So each one is a different type of energy, each one has a different type of particle. Now, up until this point, I've been using the word particle very loosely. I've been using it to describe energy levels, which is not really correct. So what I'm going to do now is, instead of discussing energy as particles, I'm going to discuss them as bosons. I'd mentioned the four different fields of physics. So within those four different fields, those four different bosons that go along with each different energy type. And these four bosons are known as gauge bosons. So the four different gauge bosons consist of the photon, the gluon, the Z boson, and the W boson. Now, what does this really mean? Well, the photon is actually a representation of the electromagnetic force. And I know most of you will probably relate photon to light. That's because light is an electromagnetic wave. So the photon is actually the particle for electromagnetic force. The W and Z boson are actually both for the weak nuclear force, whereas the gluon is for the strong nuclear force, also known as the color force. So that's the summary of the different forces. Now, if you noticed, we have four gauge bosons that relate to three different energy types, but we never mentioned gravity. Well, gravity, as we should know, is the interaction of mass over distance. Well, this is where the Higgs boson comes into play. The Higgs boson is proposed to exist. It is only hypothetical right now. It is only theorized. But the Large Hadron Collider has come very close to finding it, and it has been believed that they found it. They're just doing additional testing to make sure that it actually is the Higgs boson. And what the Higgs boson would do is it would define mass. It would be this particle that goes through everything, because mass is in everything. It would be this particle that goes through everything and is the stuff that gives mass, because we know mass exists, but we don't know why. So the proposition is that the Higgs boson is actually the particle that gives mass to objects and in effect causes gravitational force between objects. The idea of bosons is bosons actually have fields. So in the case of the photon, the field is the electromagnetic field. And the gluon, the case of the gluon is the strong nuclear field, and so forth. So the case of the Higgs boson is the Higgs field, which would be it's almost like a gravitational field in that respect. There's a lot of information on this elsewhere online. If you're interested in this, I encourage you to look it up. There's no lack of things that you can learn. You can be on for hours and not even scratch the surface. Quantum mechanics, if you get into the math of it, is very, very tough stuff. But if you just look at the theory of it, it can be very interesting as well. I hope you guys enjoyed the video. If you want to see anything next time, just leave a comment below, and I'll take a look at it, and I'll try and make something along those lines. Have a good one, guys.